So now we have another kind of little funky structure with a couple angled bars and then a two-force member between them. They are connected at point C here. So we have equal and opposite vector here where we take them apart. And this two-force member, we have equal and opposite force acting on part 1 and part 2 and part 1. There is a part 1 is connected to ground at the pin joint at point B here. It has an external, it is connected to ground through a roller against the wall here at point A. And then there is a load acting here at, in this case, it's going to be acting downward in the vertical direction, since they were told us that the angle was 0. This angle here was 0 in this case. So we can again start writing position vectors. I took A as the origin, and then so position vector to F was 20 inches to the right, to B was 8 inches up, to C was 4 inches to the right and 8 inches up, to D was 16 inches right and 8 inches up, and E was 16 inches right and 10 inches up. So we can look at all these, the forces that we have unknown in here. So we have the reaction force at C, 2 components, 1 component of the reaction force at A, this is actually, the C is an internal force. So B, we have a reaction force, 2 components of it. And then the internal force E, we just have 1 component because it's a 2-force member here. And then we have our applied load that is 60 pounds in the downward direction. So what I did is I said, okay, let's look at the whole body as together. So both parts together. So FC cancels out, FE cancels out, and so we just get A, B, and F acting. If we draw a free body diagram of the whole thing put back together. So we have force and moment balances, and it turns out then we have our 2 components of B and our 1 component of A left in these 3 equations. So we can solve for those. And we get that FA is 150 pounds, FBX is 100 minus 150 pounds, and FBY is 60 pounds. So this thing is acting over X is moving something like this over here. As we'd expect, this is pulling this down, and then this is kind of pivoting it up, and so it makes sense how the forces are acting. And so we have these, but we also want to find what FC and FE are. And so we can do that by taking, I think it's probably better to just take a look at body 2. So we have FC, actually I looked at body 1. We could either look at 1 or 2 to get these. We'd get the same answer, and it'd probably be easier to go with 2, but I went with 1. So then on body 1 we have forces A, B, C, and E. So A, B, C, and E acting. We know already what B is, and we know what A is. So we can then, these two, we have 3 components of 2 components of FC and 1 component of FE to figure out. And we get 3 equations. Okay, again, our force and moment balances for this body here. And so our 3 equations, we find out that FCX is 0, FCY is 20 pounds, and FE is 80 pounds. So FCX is 0. So this force is actually in the vertical direction. FCY is 20, so it's this way, um, and as we'd expect, because this is pulling, yeah. So basically, we have a pivot point there for FE, and that says that this bar here is in um, compression, because the bar in between is in compression, because if we do a free body diagram of the bar, our forces would look like that, and so we have compressor forces in that bar, as we'd expect, because we're pulling this down, and this is restricted from moving, so we're squeezing this in here. So it'd be a good mechanism for squeezing something